All right, so the next elevator pitch will be given by Oscar, and he will talk about ends.
Yes. Okay, thanks to the organizers for organizing this nice conference day. So today I'm talking about ends, and this is a project I'm working on with my supervisor and a collaborator in Germany. My supervisor is Maria Bruna in Cambridge as well, of course. So let's look at a video of ends first, just to get inspired. So what I like about this video is that the ends follow each other in a very structured pattern. Like they're walking along a lane. Some of them are moving in the opposite direction, but there seems to be like a persistent unidirectional lane inherent to the kind of collective end behavior. So how can we understand this? Because, okay, we've established it's interesting, but how can we study this scientifically? So, we ask a question. Let's focus on like a particular phenomenon of the ends. Like ends are very complicated. We could model everything about them if we want that we know, but maybe we should first focus on capturing one phenomena. So we ask the question, what is a minimal mathematical model that captures ends forming lanes or general collective phenomena like this? So for example, in birds, you have flocks moving. So this is kind of related to the physics background for my project, because many people look at kind of similar models and have similar collective phenomena, and they use similar techniques. And my project is applying that to this end model. So we have this question, but how to do this with mathematics? So two things I will talk about today: interacting particle systems and their associated mean field limit. So the interacting particle system is kind of a set of particles that all have a similar equation of motion. And it roughly said, in my case, we have particles that consume energy to maintain a constant speed, an alignment mechanism, and some random motion. And this then we call together a stochastic particle system. And it looks like this. I don't have time to explain all terms, but we have to focus on this term. This is kind of the most interesting part, and it's the alignment mechanism. So how does it work? You have an end or a particle at the position xy with an angle theta y going, meaning that the end goes in the direction of e theta I. And then we have the normal to this, n theta I, and the inner product with the chemical gradient, which is supposed to model the pheromones of the end. This is the chemical substance through which they interact. And then the inner product of these two terms is the drift in the angle. So if the e theta I was aligned with the gradient, then n theta I is orthogonal to gradient of c, so there will be no alignment term. So this term says align e theta I in the direction of gradient of c at the position xy. So what does this look like if we run a simulation for particles? It looks like this. So ends move towards kind of the local maximum density. So we kind of get end spots. Not lanes, but end spots in this case, in this kind of minimal model. But how to study this average behavior if we have such a large set of particles? Well, there is a method for this, and this is called the mean field limit. And this gives you a partial differential equation, which roughly says that you get a quantity f with the arguments t, time, position, and angle, of a probability of finding a particle at a certain position x and a certain angle theta. And this f is supposed to be a solution of the following PDE, which is kind of related to the equations of motions I showed earlier. So again, I'm not going to explain all the terms, but we have, again, the alignment term here. And kind of to give the next step, let's look at a video again. So this is a initial condition. This is kind of the assuming that we have uniformly sampled random positions of ends, and then we forward interpolate the PDE with a numerical method, which gives a solution in time that looks like this. So from a random perturbation, there is an end spot forming. And so this is kind of the average behavior the end model is supposed to follow for a given initial condition. And then we can ask things like, what can we say mathematically about these solutions? So this is in the realm of PDE theory. And we can show several things, which are all my poster as well. So if you're interested, come see my poster. But simply said, this model is unstable if there is strong enough alignment. So in mathematical terms, it means there's a linear instability, which means that instead of getting a homogeneous state, there is some kind of pattern forming, which in this case is the spot we saw earlier. And also, we can show that the model is non-linearly stable around the constant state if there is small initial data. So this means that if my perturbations in my video were very small, then there would be no spot forming, but the ends would kind of just homogenize and form no patterns. And we can also show that there's a uniform bound on the solutions, and this is global in time. And this means in practice that there's no blow-up of the ends, which means in our video that this spot stays bounded in time. So there's no collapse to some kind of end black hole. So that's nice to know. But we want to also know a little bit about the lanes, because this was kind of the first motivation. And after having studied kind of the simpler model, we're now focusing on a more complicated model. And this model is like adjusting the model a very tiny bit. And it's by going back to the alignment picture here. Instead of sampling the gradient at xi, we're going to sample the gradient at xi plus lambda e theta y. So you're kind of looking at the lambda, the distance from the center of mass of the end, but you're kind of looking at the antenna of the end. So this is kind of a shift in their sensing, and this already gives much more interesting behaviors. And I will show you a picture for this. So this is the particle simulation a postdoc of my supervisor did. So you see kind of ends forming if we drop ends in the middle, and then they kind of follow the lanes they form. And I also did some simulations for this, where we kind of start with ends with a polarization. So that's what you see here at t time is 0. The ends have a polarization initially and some random perturbations. And then we let time evolve. And actually, the polarization persists. So you really keep kind of the lane moving instead of just one spot where the ends are not really moving, but just kind of stabilizing each other. So this is interesting about this model, and I'm going to study this more in the future. So the prospect for this research project is to kind of look at this model and try to show some mathematical results for this, with kind of a focus on kind of showing a phase transition if you increase the look-ahead distance, the lambda, or if we can find an explicit solution, and again, kind of the stability properties. So that was all I had to say. Thank you for listening.
questions for Oscar? Yeah, Daniel? Do you really do a microphone? Just speak loud.
So just maybe I didn't hear it properly, but with the linear instability that you proved for the simpler model, can you also prove that you converge to the AND spots?
No, this is also ongoing. Yeah, you can only show that there is some convergence for time subsequences, but you need more like rigidity to show that that it really goes to one certain spot. Yeah.
Thank you.
So, I mean, you can still go to Oscar's poster.
Yes.